Hello, AI enthusiasts. Welcome to a new deep dive. Building on our previous talk about mean, variance, and standard deviation, we are now ready to tackle the heart of probability. Most videos on the expected value never show the geometric perspective of a balancing point. In this video, we want to show something different, the 3D probability landscape your data actually lives on, and how to find its true center of gravity before you even take a single sample. Think of the expected value like a physical seesaw. If we place different weights at different distances, the point where the seesaw perfectly balances is our expectation. In statistics, the weights are the probabilities of different outcomes, and the positions are the values of those outcomes. It is not just the average of the numbers, but a weighted average, where more likely events pull the balance point closer to them. Let us imagine a game where you can win $10, $20, or nothing at all. Each outcome has a specific chance of happening. If the chance of winning nothing is high, the balance point shifts toward 0. To find the expected value, we multiply each prize by its probability and add them together. This gives us a single number representing what we can expect to win on average if we played this game thousands of times. We can visualize this using a bar chart where the height of each bar represents the probability. The expected value is the horizontal position where this entire chart would balance on a single needle. Even if the expected value is a number that cannot actually be rolled or won, like $12.50, it remains the theoretical center of our probability distribution. It is important to remember that expectation is a long-term prediction. If you play the game once, you will never win exactly the expected value. You will win one of the actual prizes. However, as we simulate hundreds and then thousands of trials, the average of all those results will crawl closer and closer to our calculated expectation. This is why casinos and insurance companies rely on these numbers to stay profitable over time. One of the most useful properties of expectation is that it adds up. If you play two different games, your total expected winning is simply the sum of the expectation for each game individually. Think of it like adding two different grocery bills. The total expected cost is just the sum of the expected costs of each item. This holds true even if the gains are connected or influence each other in complex ways. Consider how insurance companies determine your monthly premium. They look at the probability of a rare but expensive event, like a house fire, and multiply it by the cost of that event. By adding this to the costs of smaller, more common claims, they find the expected cost per customer. They then charge slightly more than this expectation to cover their own expenses and ensure they can pay out when a disaster actually occurs. While expectation is powerful, it does not tell the whole story. Two different scenarios can have the exact same expected value, but very different levels of risk. One might be a guaranteed small win, while the other is a wild gamble that usually results in 0, but occasionally pays out a fortune. This is why we also need to look at variance and standard deviation, which measure how much the actual results spread out away from our expected center. In summary, the expected value is the weighted average of all possible outcomes. It acts as the balance point of a probability distribution and provides a reliable prediction for the long term, even if it never happens in a single trial. Understanding this center of gravity is the first step in mastering risk and decision-making. If you found this deep dive helpful, explore our other videos on variance to see how the rest of the puzzle fits together. Subscribe to master more core concepts of probability and statistics.